last time I gave you a motivational speech saying that when we have hexagonal lattices, we expect deterministic diffusion. And I gave you the formulas. In practice, it's actually fairly hard to work with this system. It's real work. So what I would like to do now is I would like to just get the qualitative part of the dynamics and model it with something much simpler. So this is not a real physical system, but it's as good as stuff that you learn about random walks on a line. It's it's a model of random walk on a line. And the basic thing about scattering, and the reason why Sinai got a Abel Prize and why we know these are ergodic systems is that if I start with some little range of initial conditions, so different positions and different angles, so that's a ball in our state space, two-dimensional state space for this problem, then what happens is there are some initial conditions that go back, and then there are some initial conditions that move to the left, and some initial conditions move to the right. And if I keep doing this, I'll find there are 12 different things that can happen. But the basic thing is that if you try to think of this in this strip, the motion to the left and right has to do with bouncing here and being spread around at every bounce, because it's unstable. So the basic thing is there's stretching in the system. So you can model it in the following way. You can say, well, I'm someplace here, and if I start close to the symmetry axis, I'll bounce this way, and I'll say that means I stay. I don't move around. So there'll be some region in which I stay. Now, in every bounce, this region opens up. So every finite region will stretch out. So next bounce, I might go someplace else, but just in one bounce, there'll be part where I stay. Then there'll be initial conditions here, which have a property that I'll get further to the right. And there'll be initial conditions here that say I'll go to the left. And this thing I'll assume is periodic in units of 1. So there is an unit interval from minus to plus 1/2, roughly speaking, in which my translation on one-dimensional lattice is 0. I haven't translated. Then there is another unit interval. If I land in it, I've actually gone to the right. And if I land in this one, I'll go to the left. So that's the idea of building up a one-dimensional model. So now we'll build the smallest possible, simplest possible system that has this property. And if you do numerical simulation of this, you'll get a random walk. So that's how random walks are simulated very often. You can simulate them by saying, I have a probability machine, a coin that makes me move left or right. Or you can simulate them in this way, saying, I have a deterministic machine. Depending on where I start, I move left and right. So that's one way to generate random walks. So, if you understand this thing via home stretch. So basically, let me now say, I will model this by taking a map, which is just a linear map, centered at the origin, and with a slope larger than 1. So if I have a map that has slope larger than 1, then the initial interval will be stretched out, and there'll be edges that go to the neighboring intervals. So to make it more visual, I'll take slope 5 here as an example, which means that if I go this way, I can reach as far as 2.5 units to the right. And if I go this way, I can reach as far as 2.5 units to the left. And there will be conditions which are close to this origin in which I don't leave the cell. So if I'm any place between origin and this point, in one iteration, I won't get out of it. So I stay in my neighborhood. So my n, translation parameter, is 0, this little n hat. I don't translate. If I go a little bit further, then I land one hop right. So I land the interval, it's 1 unit there. And if I'm someplace here, I actually hop 2 intervals right. But if I'm on the left side, then I stay for a while, or I hop 1 interval left, or 1 interval, 2 intervals to the left. So that's what happens on one cell. the initial points which stay, the initial points that hop either left and right, and initial points that hop two distances left and right. And now we assume that this is part of a periodic lattice, this thing saying that once I end up in the next cell, I have the same law. So the law of motion is same in all the cells. There are infinitely many of them. But if I insist in staying only in this cell, then what I can do is I can do the symmetry reduction, which I've already done when we discuss discrete symmetries, etc. I can say, well, you know, I can replace this part of the map. So here, this is the map, you know, and this is its segment, this one here. So this is between here and there, in the neighborhood, this fixed point, you stay. But now what I'll do is, I'll move this segment of the map, I'll just move it by 1, and remember, that's called reconstruction equation, that I did that. Then I have a region here, where every point in this interval, which doesn't overlap with the original interval, every point in that interval in a real space goes to the right. But in the symmetry reduced space, where I've taken the entire unit line and I wrapped it on a unit interval, it's just a fixed point. Then there'll be, you know, the 2's and minus 1's and minus 2's. So does that make sense to you? So you can either look at this map that tells you, you know, how far you hop, or you can look at a map which is only defined on a unit interval, but you remember which branch is which. So now I'm supposed to have my formula. I'm supposed to compute the mean distance, and the formula says that what I do is I look at all the periodic orbits. Now there's a very simple set of periodic orbits. This thing, this is slope 6 rather than 5, but this thing has you know, 6 fixed points. So these are the simplest possible contributions. So, and the first one hops by minus 2, so I square it. So all of them have 1 over lambda, lambda is 6. So this is what this is. It's stability of each solution. The second one goes to the left by minus 1, but I square it. Then, you know, there are 2 in this particular for 6's. There are 2 that don't go. Then there is 1 that goes to the right by 1 step, and 1 that goes to the right by a 2nd step. And it turns out, because we're using linear maps, that when you compute the shadows, when you compute all the other guys, they cancel exactly. So this is, you know, wonderful thing about linearity. It's, in principle, it's an infinite sum of periodic orbits, but because the slopes are the same, the 2 cycle is exactly the product of the fixed points corresponding to it, etc. So it stops there. So I can compute the mean diffusion, and it's this number, you know, 5 over 30. Then I do the same calculation for the mean time, and what happens with mean time, each one of them, each fixed point is a fixed point of 1 iteration. So I sum 1, this is 1, this is 1, this is 1, everybody is 1, because they're just fixed points. So I get 6 divided by 6. So it turns out mean time is 1. And that's because, you know, this is such a simple dynamic system that mean time between 2 scattering is 1 by construction. And that's it. We're in 2 dimensions, and we get a diffusion constant, and you can do it by hand. Now, the moment you understood how this works, you actually compute it for every integer, and you compute it for every odd integer, etc. So then you say, oh, well, that's okay, but what if lambda is, you know, not 6, but 7/3 or something? Then you go and, you know, realize the wisdom of the course, because it's already been done when we did discuss pruning, etc. It turns out that whenever you have a rational slope, the partition of the state space is a finite partition, a generating partition. So when you take slopes other than that, you'll discover in here there'll be some finite number of things, and if you use few periodic orbits, etc., you get everything again. So I worked out one example as the example in Kara's book. So that means that in the space of all possible diffusions, I can analytically compute the diffusion constant for every rational number. And you know, there are lots of them and they're dense. So you can study what does diffusion look like for every possible slope by approximating it by nearby rationals. So you do this, and that was a thesis work of Klages in Maryland. And he has written a very nice book and continued working in this way. So, you know, what happens in more general thing, you start finding periodic orbits, ergodic orbits, etc. That's all good. This is the calculation I just did for you. And here is the plot taken from Klages' thesis and published paper. And what's plotted here is the slope of this linear map. So it turns out if it's less than 2, nothing interesting happens. So it starts getting interesting when it's 2 or higher. And what we just computed was we computed even integers. We computed this value. Well, we computed 6, but you know, we can fill it out for all integer values. Now, when you compute it for odd ones, you'll actually get different numbers. So you'll find out that when the slope is 3, diffusion is hard, and when the slope is 4, which is very counterintuitive. Statistical mechanics predicts a smooth curve with a wrong, you know, just wrong curve. But anyway, you know, monotone and wrong. And then you do it for the fractions, and you start finding, you know, this is complicated. And in this, that's funny. I see it. Well, if you look at this in the book, it looks better. But in the book, he has enlarged various neighborhoods. So what happens between 3 and 3.1, very small neighborhood here. So it turns out at 3, this thing goes up, you know, in small units from 33 to 0.365, and does something complicated and does that. What happens between 3, 5, and 6? So what happens at this interval? So in this interval goes down, does something up. What happens at 5.6 to 5.66? So you look at a little interval that seems to have structure and does something there. In other words, no matter where you look, this thing is never smooth, never differentiable, and it's a signature of chaotic dynamics. You couldn't get this from any stochastic process. This says that hidden behind this thing is a perfect array, and you're measuring properties of this perfect array in terms of transport through it. The next thing that you can do, because it's also easy to do, so I think I've given it to you as an optional thing, but it's just easy to do. You can compute higher derivatives. So it turns out because of this map was antisymmetric as phi goes to -5, x goes to -x. Left and right were equally probable, so all the odd derivatives you can show they're 0. So you only care about even derivatives. The second one is what we computed, that's diffusion. This fourth one is called kurtosis, or it has, because you know everybody invents it, it has a zillion names, but net coefficients, there are connected, not connected, Green's functions, 4 But anyway, you can just do the calculation. And what happens is you get this thing to be non-zero. You know, it has some analytic dependence. This is done for odd m's, odd slopes, I think. Maybe the slope is, lambda is 2 times m, I forget what it is. And, you know, this thing is non-zero, except for a few special values. So this process is not Gaussian. So if you do numerical simulation, it'll look pretty Gaussian. But you can actually analytically show that it's not Gaussian. So chaotic dynamics, though to the vulgar eye looks like a random process, is nothing but. You know, everything about it is specific and remembers everything about dynamics. So to summarize, here is how we got to that. We went from dynamics of a single state to dynamics of distributions of states. So we started looking at functions on a state space and these final evolution operators, and then we started describing what measurements we make. So, you know, we are measuring displacement in this set of examples, how far I got in the space by dynamics. And we define evolution operators, etc. And there was one idea. So the first idea is give up individual trajectories. That's stupid. Look at densities. That turns the problem into a linear problem in infinite dimensional space. Second idea, you know, look at things that are additive, stick them into exponent. So weigh your results by exponentiating them and what happens. The next idea for this particular application was that if you have a regular lattice, or almost regular lattice, but in this case, exactly periodic lattice, we can reduce it to dynamics on a compact domain on a single tile. And now our machinery works for single tiles. And then the theory says there are beautiful formulas in which you average in a non-trivial way your observable on products of all prime periodic orbits weighted correctly, basically by their instability, but with minus sign. And you get beautiful exact analytic formulas for things that you want to predict. The example I gave you was on a lattice, but I think we should scratch our little heads and do it more generally. So I had some problem that I didn't understand. To compute diffusion, whenever I found an orbit in a fundamental domain and its continuation in a larger space, I used 12 copies of it, and then I computed diffusion constants in the 2 dimensions. I think that was not smart, so we have to figure out how to do this. The other thing is this symmetry could be continuous, while we looking at discrete case. But the formalism should work, because we know how to quotient continuous symmetries. And what I will do next week, so this is an application, and I'm sorry, applications of nonlinear dynamics are all very hard except a few of these linear maps, etc. So I don't emphasize in this course applications as one would do in atomic physics course, etc., because every example is really hard. But the theory is very beautiful, and what I want to now do is I want to tell you that the theory we developed of how symmetries affect dynamics and why we have to reduce them, we've actually forced to do that theory by the periodic orbit theory. It turns out that we have to do that. And what will happen is it'll very much like quantum mechanics. What will happen is that because now we look at linear operators acting on spaces, spaces have symmetries, irreducible representations of the symmetry block diagonalizes operators. And it makes all calculations much easier. And it turns out that that thing that's just like quantum mechanics forces us to look at a reduced state space. So in case of discrete symmetry, it wasn't just that it was convenient for me. It actually turns out that the way you compute this, it's like computing spectrum of helium. You have to write as a product of ortho and para, and they're separate, so determinant block diagonalizes, it becomes product of determinants, and every calculation is much easier when you do that. So that's what I'll do for the rest of the course.